Hello YouTube, welcome back to another video. In this video, I will talk about something I don't normally talk about. Science, specifically kinetic energy. If there are any calculations that you want to do yourself, it is actually surprisingly easy to do so. The formula for kinetic energy is kinetic energy equals 1/2 times mass times velocity squared. One thing to note is that anything with mass is in kilograms, anything with velocity is in kilometers per hour, and anything with energy is in joules, almost 100% of the time. But for this formula, it's always the same. If you use the wrong units, you will get incorrect answers. And that's why NASA's Mars Climate Orbiter crashed into Mars. But anyways, let's start with the video. I will start small and build up to bigger things. The first thing, atoms. Every moment you're constantly being bombarded by air. Unless you're in a pool, then it would be H2O or water, which is mostly 79% nitrogen and 27% oxygen. A nitrogen atom weighs only 2.326415 e negative 26 kilograms, or 0.00023266415 kilograms. An oxygen atom weighs this. At room temperature, atoms move at roughly 500 feet per second, or 548.64 kilometers per hour. If we plug that into the equation, then you can see we get an astonishingly low but unsurprising. I later learned in school that I used the word astonishingly wrong, but I decided to keep it in. Also, everything is so scripted. This message is scripted. It's even so scripted. 6.38182168 times 10 to the negative 24th power joules, or 0.00638182168 joules for the nitrogen atom. And oxygen is this. For reference, 1 pound of TNT is equivalent to 4.184 million joules. Now, you may think that's not much, which it's hardly anything, but only zero can be zero. The atmosphere at sea level has a pressure of 14.8 psi, which means for every square inch of surface area, 14.8 pounds of force are being put on an object. That includes you, but you are so used to it that it feels normal. All of that's just because of air. Now, the next thing I want to see is how much energy is needed to break a bond between two hydrogen atoms. So first, let's get H2. Now let's throw stuff at it. Although we do need to know how much energy is needed to break an H2 bond, which is 7.24 times 10 to the negative 19th power joules, or 0.000724. If we compare it with the numbers from earlier, that already looks much bigger. So we can probably skip all of the weak atoms. No. Wait, you. Gold. Pretty heavy if you've ever touched it. So let's throw it at an H2 molecule. Gold has a mass of 3.2707635 times 10 to the negative 25 kilograms, or 0.00000000000. I'm getting sick of saying that. It's just the number on the screen. Assuming someone accidentally dropped a gold atom into the air,
it's worth about $5,700, and it's one of the most expensive and precious things that I own. I should say, though, that the gold hasn't actually vanished, and it's just in a water-soluble form called chloroauric acid. It's actually very easy to get the gold back, and I'll show you how to do that in enough. Oh no.
And it is moving at 548.64 kilometers per hour. If we plug that into the equation, just barely short. Next up is Einsteinium, named after the man himself. The most stable isotope of Einsteinium, Einsteinium-252, has a half-life of 471.7 days and a mass of 4.1846 times 10 to the negative 25th kilograms, or that. Again, it is the very likely scenario that someone drops an atom of Einsteinium into the air moving at 548.64 kilometers per hour. If we plug that into the equation, no. Okay, we probably need to make it go faster. 700 kilometers per hour? No. What about 800? No. 1,000? No, but we're getting there. We have reached 2.0923 times 10 to the negative 19th joules, and 7.24 times 10 to the negative 19th joules are needed to break the bond. Okay, let's try 1,200 kilometers per hour. No. Dang, this thing is so strong. Let's just jump straight to 1,500 kilometers per hour. Nope. 2,000? Finally, man, we just barely broke the bond with 8.3692 times 10 to the negative 19 joules. Now, the next thing I want to cover is how much energy is released in a supercollider, because the answer is probably a lot. Assuming every stream of atom is going 99% the speed of light, and every beam has 2 million atoms, you can see how that would be a lot of energy. A lot. Let's pretend that the people running this supercollider want to find element 104, which has not been discovered yet. We can name this element Tony Stark in honor of him making a new element in the Iron Man series. The people will be combining element 52, because 52 plus 52 equals 104, which is tellurium. In kilometers per hour, the atoms would have a speed of 1.068 times 10 to the 11th power, or that. If we do the math, then just one atom will have approximately 0.001208404444058 joules of energy. That will give us 2,416.8 joules of energy in total. For reference, 1 pound of TNT has approximately 4.184 million joules of energy, and a skydiver has an energy of about 1.44 million joules. Anatoly Petrovich Bergorsky survived getting hit by a beam of protons, which released an amount of energy equivalent to 259.2 joules. The protons hit his brain, and the side effects of this are that part of his face is paralyzed, he is deaf in one ear, and has epilepsy. So getting hit by our theoretical beam of element 52 would have 10 times the amount of energy. I'm not a scientist or doctor, so I don't know if it would be 10 times worse. I just know it would have 10 times the amount of energy. Now I want to finish this video off with something big. So how much energy would a 10 kilogram weight going at 99.99% the speed of light have? And wow, that's a lot of zeros. Anyway, please subscribe, like, and thank you for watching. Also, this script happens to be exactly 1,000 words. Anyway, thanks for watching the video.